Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome everybody again to another episode of our show. Today bringing you another fascinating guest who is helping to create a better tomorrow. We have the honor today of being joined by Dr. Doug Willard, who is Program Element Manager, Game-Changing Development Program, the Space Technology Mission Directorate at NASA. And the Game-Changing Development Program is focused on advancing space technologies that may lead to entirely new approaches for the agency's future space missions, provide solutions to significant national needs. The organization collaborates with R&D teams to progress the most promising ideas through analytical modeling, ground-based testing, spaceflight demonstration of payloads and experiments, and their efforts are focused on mid-technology readiness levels. So generally from taking things from the lab concepts to complete engineering development prototypes. The program's investment in innovative space technologies ultimately directly supports NASA's mission to drive advances in science, technology, and exploration to enhance knowledge, education, innovation, of course, and both economic vitality and stewardship of the Earth. Game-changing development focus on transformative space and science technologies that will enable science missions and NASA's future Artemis program back to the moon. And additionally, their technology development serve as a stimulus to the U.S. economy, providing inspiration and opportunity to our next generation as well that will be taking over the leadership in this area. Previously, Dr. Willard was the Deputy Division Chief of Laboratories, Development and Testing Division at NASA's Kennedy Space Center. He served in many leadership roles at the Kennedy Space Center, including Chief Engineer for Research Technology Development and Branch Chief of Engineering Analysis Branch within Engineering Directorate. He also served for many years as a research physicist in the Kennedy Applied Physics Lab. Dr. Willard received his doctorate in physics from the University of Central Florida. A lot of exciting topics to get into today. Dr. Doug Willard, thank you so much for taking the time to come on our show.
Hey, thank you very much. I appreciate it. That was a very nice introduction. Glad to be here.
It's great having you, Doug. I would love to start off, as we typically do, by handing you the floor for a little bit, just to talk a little bit more about yourself. If you could sort of take us back a bit to everything from where you grew up, when you got interested in STEM, when you got interested in physics, and a bit of this early career journey at NASA. I think that'd be a great way to get things going.
Sure. Okay. I'll take a few minutes here, I guess.
Please.
So it started, for me, it started back in engineering school. So I started life as first a chemical engineer and then a mechanical engineer. And that's what drew me in, building stuff and breaking stuff as a kid. I had one skill perhaps, and I was curious. If you would say, like, what's my superpower, is that I'm inherently curious. I can look back in time and look back when I was a little kid, and I'm not appreciably different than I was when I was 8 as far as curiosity goes. So if you're looking at, like, well, how did you get from here to there? I just never stopped asking questions and being curious. So that I'm just inherently that way. But again, back to the engineering. So I started a life as a mechanical engineer at NASA. I was at the time they called them co-ops. Now they call them interns. And so I was a co-op and did machine design. So I was a aerospace mechanisms designer for approximately the first third of my career. And that was really great fun. I got to work on some really interesting programs. In addition to shuttle, I got to work on the X-33, which was a single stage to orbit lifting body, if you're familiar with such things.
Okay.
Takes off horizontally, or vertically, lands horizontally.
Mm-hmm.
And then there was another one that was for Lockheed. I was able to also work briefly on the Delta Clipper. That was a McDonnell Douglas version that took off and landed both vertically, both really interesting. So I got to spend a good bit of time in that world. As it turns out, about 2 years after I graduated, and I'll try to keep this short,
Take your time. Take your time.
Okay. Well, about 2 years after I graduated, I went back to graduate school, and what I found out when I went into as an engineer, I found out what I really liked about, or maybe even loved about engineering, was actually the theory. And
Okay.
you talked about PhD, and my PhD is in physics. Well, I didn't start life as a physicist, but it turns out that's what I love to do. I really love math. I made my living at engineering, but I loved math. I loved physics. So I went back to school right away. I went to school a really long time. I was a professional student. I kind of used my job, paid for my physics habit. So I went to school for a really long time and got several degrees in that area. And in physics, I did something very different. I studied theory. So I'm a theorist when it comes to in physics. There's usually two camps: experimentalist and physics.
Sure.
Theorist. I'm a theorist. So it was an interesting combination between machine designer, engineer, and how I'm making my living, and then in physics. And in about 2019, somewhere around 99, 98, something like that, I actually switched careers. I actually went and started, honestly, I put down my engineering mouse and I picked up my physics mouse. I changed computers, went over to the applied physics lab, and then spent probably the middle third of my career in the physics lab, applied physics lab, and did research there. My specialty in theory is fractional quantum Hall effect, which is a theoretical pursuit in a two-dimensional plane and a very strong magnetic field that's transverse. You can get it'll essentially lossless currents at very specific, what's known as filling factor. I don't want to get too deep into that, but it's a very interesting topic theoretically back in the day. And I, in the physics lab, I worked many different projects, typically coming up with technological applications, applied applications of physics principles, sensors, optical solutions to shuttle, station, and other programs. And so that's how I made my living for the middle third. And then at the end of that, I had some opportunities to work in analysis. I went back to pure math, and so I worked with a group that covered, with the exception of like electrical or chemical analysis, just about every other analysis pursuit that we do in most of our programs, space flight programs. And I led that particular group, and I'm not an analyst per se, but I speak math, and that's the common language. So I kind of parlayed my love of math to that. Eventually, that became the chief engineer. So I was a chief engineer for research and development for quite a while and just recently I moved for this last year to GCD, game changing development, as you mentioned, to specifically target frankly, to do something that I don't have skills. By most people's measure, I'm a technical person. And so I'm weak in certain areas. I never did system engineering. I never did project management. And I wanted to get good at that because I felt that I could bring something to the table. So you work on well, I don't know if you do, but I try to work on my weaknesses. And I was like, well, that's a big hole of mine. And I'm not looking to be the best person in contracts or the best person that's a project manager, but I know I can get better at it. And so I would be better for it overall to gain that skill. So that's what I'm doing right now, and trying to help PIs with getting through their hoops inside of research, and for the last year in GCD. So
Awesome.
that covers that covers a big, for 34 years I was a technical guy. In the last 1 year I've been trying to help technical guys.
Absolutely, and we need that though.
Yeah,
No,
absolutely.
no, I appreciate all that. That's a fascinating background story. Yeah, as I sort of sit back and I read the Space Technology Mission Directorate missions, or developing transformative space technologies to enable future missions, and then sort of identify and rapidly mature high impact capabilities and technologies, and to investigate innovative ideas and approaches that have potential to revolutionize future space missions. And then I talked in sort of the intro about GCD and this sort of mid technology readiness level. So you're not thinking of getting us to Alpha Centauri anytime soon, but you're working on these nearer term things that, as we go back to the moon, as we start thinking about Mars, we got to have some of these tools in place. It's not just about sending the rocket up. Talk a little bit, if you would, about STMD, the GCD, and a little bit about, I'm sorry, aside from talking to really cool people like you on the show, most of my experience at NASA is, of course, from Hollywood. But talk a little bit about sort of your typical day. Sort of where do your directors, and we'll go into some of the portfolio and some of the things I peeled out there, but sort of where do the directives come from? As hey, Doug, we want you to work on finding us water on the moon today, and ideas on that front versus fission technology. Talk a little bit about sort of how everything fits together in a given day for you, if you would.
Okay. Well, I think I'll. You mentioned something early in that like a little bit of an overview of STMD and how I maybe fit into there, and how those ideas percolate down into the. Okay, perfect. So STMD is one of the mission directors. When you think of technology development, not that technology development can't happen or doesn't happen in the other mission directorates. This one's, it's in their charter. It's what we do. And certainly innovation happens across NASA. It's a plug for NASA. It's a fantastic place to work. I mean, I spent my entire adult life working in NASA, doing development, specifically most of it in R&D. And I just feel super lucky. I mean, I don't want to gush too much, but it's whatever you think it is, it's exactly that. It's exactly what you think it is, or it certainly can be, and what you can make it. And so within STMD, I'll hit on the two that I know the most. There's other ones out there, and we're going to talk about GCD. I'll get back to the GCD. That's going to be your mid-level, right? So that's, you're looking at TRLs. Well, I don't want to go blasting past TRLs. Should I talk about TRLs?
Sure.
Or okay. So TRLs is a scale. It goes from 1 to 9 that we use within NASA, and actually it's used in industry and in academia in different countries all over. But it was something that was developed in NASA quite a while ago, and it goes from 1, which is the low TRL. If you talk about low TRL, that's going to be high risk, theory, blue sky. You almost want to be crazy ideas out there. I don't want to say crazy ideas, but if you present your idea, and I'll give you an example. I happen to work. I'm a principal investigator in they call them fellows in the NIAC program, and the NIAC program targets low TRLs. You're looking at 1s, maybe 2s, but pretty much 1s and 2s. Okay. And so some of the research that I do there is in a project called solar surfing. So I'm a phase 2 solar surfing. And my goal with that, I'm going to give you just an idea of like that kind of TRL and what we're looking at there, which is, when I say blue sky, that's way down the line. That's something that is high risk, high reward, mission based. And solar surfing is the idea is, how close can we get to the sun? Specifically, I'm interested in something called the transition zone, and I'm also interested in other aspects of the sun. And the technology is, in that particular case, takes a material that is it's not just it's a highly scattering material. So the photons come in and they bounce around, and they want to come back. In fact, I just went to the lab today, and there's a thing called absorptivity, and absorptivity is how much light is going to be absorbed, or it's not just light, but it's electromagnetic waves. There's going to they'll transmit energy. It'll heat you up.
Mm-hmm.
And absorptivity of this particular material is it's formed with 200 to 300 nanometer particles that are centered, meaning pressed together and heated up in a very specific way to maximize the scattering. And it turns out it does scattering really, really well. It uses actually the same principles that white paint uses.
Okay.
If you're familiar with white paint, if you're wondering why is white paint white, well, it's because of the scattering. And and as it turns out, the absorptivity is actually really, really minute, less than 1% of the energy. So what you can do is you can take that, put it on a shield, and you may be familiar with one of my favorite missions, which is the Parker Solar Probe. Parker Solar Probe is circling Venus and the sun. It just went through another very close pass of the sun here just recently, and they're getting very close. But I want to get closer still. And one way that you could do that is to either be able to absorb the material, heat with your material, or you can just not take it on. And so those are the kind of the two different things. Either we're going to go in and we're going to be rugged thermally, or we're going to just not take on the material and we're going to reflect it. So those are the two different approaches. And my approach is the reflecting kind. And so right now we're working on getting, to give you a sense of scale, Parker is at about 8 or 8.5 solar radii. So if you took the radius of the sun, how far are you away from the center of the sun? About 8.
Okay.
I like to talk in terms of numbers that I can count on my fingers, because I think it's a little, because if I say the solar radius is 700,000 kilometers,
Right.
I don't know if you get a feel for that.
Right.
But if you kind of get a sense. So my goal is to get within 2. Now, I kind of went down a little bit of a rabbit hole, but you can imagine that is a far-reaching technology to come up with a mission that could take decades, plural, to get to that happen. So I'm being in my 34th or 35th year with NASA. I'm not likely to see that mission as a NASA employee. I hope to see that someday, and that's what I want to see. But that gives you an idea of future down the road, far-reaching technologies, and that's on the one side. So that's NIAC. We cover the full gamut. Usually it's up to 7 is usually our target. After 8 and 9 are more operational. So you're doing, it's going to be implemented in the mission. So usually I think of 1 to 7. There isn't an 8 and a 9. But what we're going to target in GCD is your 4 to 6.
Got it.
Maybe your 7, something in that region. Maybe we'll go as low as a 3. Let's not split hairs here, but we're in that middle region.
Got it.
And what we want to do is take proof of concept, lab proof of concept, like this technology has some connection to a possibility of working. And we want to get that into space, into a mission, get it qualified, quantified, codified, so that you can actually take that and go to a mission or mission manager and say, hey, we have this technology and you have a gap. This is your solution. So our goal is to get it into practice, into actual missions on a regular basis. And that's where GCD comes in. We want to take it from the proof of concept through what we call the breadboard phase, through the brass board phase. We're notching up the TRL. So you're at 3, 4, 5, 6, and then 6 and 7 is when you're launching it and putting it out there so that you can qualify it as a flight qualified piece of technology. So that takes you through the TRL. Now, as far as GCD goes, we're targeting those areas. Now, I'm what they call a PEM, an element manager, program element manager. And so for me, I look at currently about 14 or 15 projects, some of them related, some of them not related. They're very diverse set of projects. And I guess for this purpose here, I could talk to you about some of the different kinds of technologies or the kinds of projects that I work on, and what we're doing, how we're doing it, why we're doing it, and kind of give you a sense for, hey, this is what GCD is about, this is what ST&D is about, this is what we're trying to accomplish as a mission director and as an agency. And you did ask before, how do these ideas come to be? Like, why are we studying materials? Why are we trying to develop ways of producing parts in space, manufacturing parts in space? Why would we want to discover water on, not just discover water on the moon, but quantify the water on the moon? Go in there and actually get the constituents. And so I'll tell you about some of those projects, but how do they come to be? They come to be, I think, initially through the administrator and the administrator of the entire country, and then also the administrator of NASA. And within NASA, we have directives. We're going to go do exploration, in this particular case, on the moon. That is my goal. I want to go and do that. And to do that, you have to certainly have your tried and true technologies that you're going to use, chemical rockets to get there, and there's all the communication, and there's myriad of things that you're going to have. But you also are going to need to develop technologies to fill gaps.
Yep.
So I need to go do something, and I currently can't do it, but I'm really close to it. And so those gaps are going to be collected from the gap holders. And there's a group of people called principal technologists, and different principal technologists are going to be over certain areas like structures or thermal or propulsion. There's I think 14 of them. Yeah, you'll have to check me on this. 14 or 50 of them in the taxonomy of technology. There's these different, we'll call them swim lanes of technology that they group them in just to have some way of organizing them. And these principal technologists are going to be over one or two of these areas that they're expert in, and they are tied into the people that have needs, people that have problems that need to be solved, that have gaps that they're looking for technology to fill. And so they have these together, and they put them in the swim lanes, and they organize them, and then we'll say, okay, as a mission director, we're going to need X, Y, and Z, and there's a big long list, and they will put priorities and resources toward particular areas that they think would be most beneficial, most efficient way of using our time and money and resources to solve.
Got it.
For us, we want to go to the moon. We want to do exploration, moon and beyond.
Yep.
And to do that, as an example, we're going to have to have have to get better at using resources that are existing already on the moon or wherever we're going to be. And in situ resource utilization, you'll hear that acronym ISRU, in situ resource utilization. So these are using the resources in the places that we're going to be exploring. And the reason for that, just to boil it down, is that up mass, meaning mass that I have to take with me, is going to be a huge limiting factor in exploration. And I'm sure that I'm not like breaking new ground for a lot of your listeners here, but I just want to kind of frame the problem for those that may not be aware of it. And so when you look at the game, we have chemical rockets. They're of a certain size, and they can have a certain up mass. And if you look at the mission plan, the architecture of how you would set up a base on the moon, or how you are going to do exploration, this is for architects that put these missions together. You're going to run into pretty quickly, mass is a big limiter. It's taking it with you. So it doesn't take very long to figure out, okay, we're going to have to use our resources out there. And those can come in different forms. Those can be getting water. Those could be getting fuel. Those could be using, in this case, regolith, which is the dirt. It's the non-organic dirt of the moon. It's the moon dirt. And they call that regolith. So if you were to use the moon rocks and dirt and dust, the non-organics up there, to construct, for example, landing pads, or constructing berms, so that you don't, when you land and you take off, you do not demolish your neighbor sitting next to you because we don't happen to have conveniently located launching pads, both to land and to take off. You're going to need power, you're going to need water, you're going to need fuel, you're going to need materials up there. And in a real way, you're going to have to go figure out how to explore, mine. You're going to have to process it to make it into a form that is usable. For example, if you wanted to make metal, maybe you could mine, extract out of the regolith metal, put it into a form that is usable. Let's say a wire, and you're going to use that wire, and we're going to use some welding process. Well, all of that would need to be developed. And there are other things, and I'm just going down. I'm not going to cover all 14 things, but that's what I'm looking to do. And so the ideas come down from technology gaps, people that have missions, and then we say, okay, we're going to attack X, Y, and Z because that's in our wheelhouse. We know we can do it. If we got a promising TRL-3, a promising TRL-4, we just have to ratchet that up the TRL level so that we can take that and put it into practice.
Awesome.
And give that to our the people that are going to put that on the moon. So I was gonna go over. I'm looking down my projects, and I was going to kind of bucketize them into two different buckets. If you thought that would be if that's acceptable.
Yeah, I mean, Doug, go in any direction you want. I mean, I had outlined when I was going. I mean, it's a fascinating portfolio, and I recommend anyone listening or watching to the show to take a look at Game Changing Development. I mean, I had outlined here in my notes Prime 1, so Polar Resources Ice Mining Experiment. I have a note about robots and telerobotics, and just because we've touched on some of the, not touched on these specifically, but gotten into some of these themes, and then lastly, of course, fission power. So it's sort of ways to resources, energy, and some really cool robots, so we don't have to put humans wherever, Jupiter. But you don't have to talk about whatever you feel like talking about that's really cool that is in your specific. Yeah.
Prime 1 is good. Prime 1 is good.
Awesome. Let's go there.
I'm going to talk about the IM2 mission, which is in Intuitive Machines.
Okay.
It's their second mission. Intuitive Machines is one of the commercial launch lander providers. So these are commercial businesses that are going to have landers. And IM, which is Intuitive Machines. I'm sorry, I talk in acronyms all day long. And
no, it's fine. Learning something.
I have 3 projects that are going to be our technology projects, GCD projects, that are going to be on that particular mission.
Awesome.
You mentioned Prime 1, and Prime 1 is it's a payload there are 2 different parts to that payload. There is a drill part, so, and I'll talk about that, and then there is a mass spec part, and I'll talk about that.
Okay.
But I want to kind of bucketize them. So you got Prime 1, then you have what we call LTE. And LTE is a communication protocol, 4G. So what you have on your phone, 4G, is being developed by Nokia, the people that make phones.
Okay.
Or make technology. They do a lot more than that. But they are providing a technology they're developing, playing on their, we're leveraging their vast knowledge in the 4G arena to have 4G on the moon as a communications way of communicating, so that instead of some of the slower, lower bandwidth types of communication that we've had in the past, you can have 4G, which is going to increase that tremendously. And I'm not using 4G flippantly. It's the same technology on your phone. And then there is another one that IM, again, Intuitive Machines, has called a hopper, which is going to be a device that is going to demonstrate that it can have relatively short firing of ways of thrusting, lifting off, and going large distances on the moon. So if you landed in one location, I can then hop to another location and yet a further location, so that you can have far-reaching. You can reach far away from your landing site, And this is another technology that's going to be demonstrated. So those are the 3 projects.
Cool.
And the idea of this, the primary one of that is Prime 1. We're going to go to the south pole of the moon, and where we believe water is going to be located. We're going to land on a lander, come down with the IM lander, and this Prime 1 payload has 2 different parts I mentioned. One of the parts is a drill, and Honeybee is the company that's going to be is going to drill. It's going to drill down a meter deep, and it's pulled back up regolith, and the hope is that we're going to find amongst a bunch of regolith, meaning the dirt, if you will. We're going to find volatiles, specifically water. Water is crucial to exploration for a variety of reasons, but we want to find water. And so we're going to take that and we're going to put in the other part of the payload, which is a mass spectrometer. And the mass spectrometer, you put chemicals or put material in there, and it will tell you the constituents and the degree and the amount of constituents that you are putting in as your sample. So you could, amongst other things, determine if you have water and how much of water. And you could also determine other kinds of volatiles. For example, if you needed propellant, and methane was one of those propellants, then you have a C and 3 H's there. That would be another possibility that you could and there's a bunch of different constituents that you could find. So that's the Prime 1, and we're going to go to the South Pole, and this is the first of this kind. And having a mass spec and demonstrating that you can go somewhere, look at material, bring it up, and tell me what is out there is a big deal. If you are going to use ISRU, if you're going to use institute resources, you have to know what resources are there and how much of it. So this Prime 1 it's the tip of the spear. It's really, we're going to go out there, we're out in front, and we're going to figure out how do we determine what is out there. And this technology is going to be proven out. The LTE is kind of almost an obvious need. If you're going to be exploring, having far-reaching, distance communication, and also larger bandwidth, having communication, protocol and ability to do that is going to be fairly key. And I think people can get behind that because they're familiar with their cell phones, and you go, yes, it's 4G. It's what you have right here. Is it working for you? If so, yeah, it's going to work for us there too. And they're going to have their hardware and software on these different pieces at the lander itself. They're going to be communicating with the hopper. And so they will be in communications with each other, and they'll prove that out as well. All of these have to be proven out. You may say, well, we have 4G here. What do we have to do? What's the big deal about doing it on the moon? It's just in the moon. There's no air, but do I need air? Well, there's a lot that goes on in going into space, and not the least of which is you have to deal with high energy particles that would otherwise destroy or certainly disturb your chips or your electronics that we don't have to, or at least for a large part, we don't have to on Earth. So get something that's radiation hardened, meaning it's resistant and resilient to and can recover from damage or disturbances that you're going to get from radiation, high energy particles, is no small feat. That is actually a big challenge. You say, well, you can put this chip up there. Yeah, well, what if the chip doesn't work? So developing that technology, that hardware and the software, is more than just the 4G you might think.
Sure.
And so it is a challenge. And then on the hopper side, do we have chemical or cold jet or other means of having a firing into a rocket nozzle? This is yes, it is. However, have we done that in the environment, in the relative environment that we're going to be on the moon, for example? No, we have not. And going into the actual, what we call relevant environment, or operational environment, even better yet still, and proving out that your technology actually will perform as designed or as required. That's very important, so that you can rely on, you can put this into a mission and it's going to work. So that all of that work has to be done. the space business is it's a fickle and finicky thing. You have to be very measured, very exacting.
Mm-hmm.
You want to. The purpose of these tests isn't to prove that it works. You're trying to
Right.
break it.
Right.
The purpose of the test is I'm looking to break this. I'm not hoping that it breaks, but I don't want to find out that it breaks when I need it.
Right. Right.
If that makes sense. So
Yeah.
some people say, well, I want to prove that it works. Well, what I want to do is see if I can break it so that I know that it works.
Mm-hmm. Mm-hmm.
And so that's what we're doing. And so that covers you for the IM2 mission, which are those 3 technologies.
Mm-hmm.
And I will do another one, which is, I'll do one on in-space manufacturing. They call that ISM.
Excellent. Okay.
Okay. There are 3 projects on that one as well. One is, I'll just give you the acronyms: ODM-M, ODM-E, and R&R. So it comes down to the E one. It is looking to produce electronics, multi-layer electronics, sensors, or just multi-layer electronics in general, additively, meaning think of a 3D printer,
Mm-hmm.
and we're going to take that in microgravity up on station and produce sensors, flexible sensors or other kinds of sensors, electronics, not just single layer, but multiple layers I mentioned. And the reason that you need to do that is that if you think about exploration, the logistics involved of all of the parts that could and will break, it's not a really question, it's when will they break?
Mm-hmm.
I'm going to need spares.
Sure.
I'm going to need to replace those. I'm going to need to fix them. I'm going to need tools to do all of that sort of thing. And if you consider, if you go out in your garage, I don't know if you work in your garage or you work at a shop, all of the different tools, materials, the machines to make all of these things, the welders and the lathes and the mills and all of these things, there's a tremendous amount of overhead to make one part.
Yep.
The alternative to that, or one alternative to that, is bring everything you need. Well, that's not realistic either, because I would need an entire parts store
Mm-hmm.
of parts full of things, because I don't know what is going to break, so I have to bring everything.
Right.
And I'm going to need multiple copies. And I can maybe do some statistics on that. I can do some be smart about what I bring. But in the end, I'm going to have to bring way more than I actually am going to need, because I can't predict. This is all statistical failures. So another option is, can we go up there with material, a 3D printer type of device, and make what we need? And so the thought is, well, that's a much more efficient way of producing whatever it is. And if you couple that with ISRU,
Mm-hmm.
meaning I can now get the metal, or I can now get the material, whatever I need. Now you're talking about long-term deep space exploration as a much more viable option. And so there are 3 projects. One is for electronics, I mentioned. Another one is for metal manufacturing. And so they're going to have 3D printed metal parts, and that's a separate technology. Just think about you're just additive manufacturing, meaning I'm starting with a base. If you're people are familiar with this on the PLA or plastics,
Mm-hmm.
or maybe even it's a very similar technology that we're going to be using in space. And we said, well, hey, the technology, I can go buy a 3D printer. Yes. But again, we have to work on the rat hardening, on the, there's
Yep.
all sorts of things that we have to worry about that you don't have to worry about on the ground. And then R&R is research, reuse and recycle. And that is,
Okay.
we're going to have materials up there. We're going to have waste. We're going to have trash. We're going to have parts that are no longer useful. And can we use those? We already have paid a great amount of cost, both monetary cost and mass cost, to get whatever it is up there. So it would be reasonable to want to reuse that, recycle that if it's all possible.
Yep.
So there's an effort to do the modeling and simulation and determine how many times can a part be recycled, and what do I get? What are the material properties that I get out of this recycled material that I might want to reuse in my 3D printer or elsewhere. So those are the three different technological projects that we have, again, between 3 and 6, 3 and 7, depending on how you want to cut it.
Mm-hmm.
So they'll give you an idea of 6 different projects in kind of 2 different areas.
Yep.
One on the moon, proving that out. And the ISM, the in-space manufacturing, that's actually going to happen on station, onto the International Space Station. So we're taking those up to station. That's in about 2024, 2025 range. So that's relatively near term. The IM2 mission is in a year, actually less than a year.
It's exciting.
That's on the manifest, and so that's going to happen. So they kind of give a sense for the scale, the type, where we're going. You can see why we're doing it. Why are we studying this? I think that I thought that could give you a feel for all of those pieces of information of what is STMD about, what is GCD about, why are we doing what we're doing.
It's completely fascinating, and it must be extremely satisfying to you too, Doug, to see your projects get up there, whether the space station or the moon. So that's it's really exciting times, no doubt. As a program element manager, or PEM, as you were saying, as you manage these various projects, I know you mentioned a company before that was involved in, I think, the Prime 1 project, but I read a little bit about, you have sort of different funding models. You have a certain prize competitions. There's a tipping point fund that NASA has to push some of these over the finish line. Talk a little bit about sort of how your organization works. If I'm a promising space tech entrepreneur, that I have a good idea here that could fit in with the GCD time horizon. How do you go about working with companies or university labs to push some of these discoveries across the finish line?
Okay, so I'm going to pull on I'll pull on at least 2 things. One of them is something called a tipping point.
Yep.
A tipping point is a category of project, and some of the ones that I just mentioned are tipping points. Actually, LTE. It's actually LTE-TP for tipping point, and that is being done by Nokia, as an example.
Yep.
And there are other ones. Hopper is also a tipping point, but I'm going to focus in on Nokia.
Okay.
So you're probably familiar with Nokia as a company. They have a long history of understanding and utilizing communications technologies, in particular 4G.
Yep.
And so we recognize we need communication on the moon and beyond, and we want to improve that. So the idea was, okay, well, we could go develop this in-house, and it would take us a long time because we aren't Nokia within NASA, and it would take us a tremendous amount of money because we don't have the infrastructure, or we would take us a long time, a lot of money. That's the short story.
Mm-hmm.
But if we went to a company and said, look, we're going to put a call out, and we want this communication technologies, and we'll quantify that and say this is what we're looking to do, and this is why we're looking to do it as a call, meaning we're going to solicit proposals, and that goes out to the world, and there's various means that those go out. In fact, just recently a tipping point call went out asking for various proposals from companies, and so the proposals come in this case from Nokia and from others, and those are looked at, reviewed, and assessed, and there will be a selection of a particular company and say, okay, well, we are going to select, in this case, Nokia, to develop this particular technology. And what we're going to do is we're going to give them a good chunk of money to develop the technology that we need. But the model is that the company is also going to put up money, not to mention they have a huge amount of of infrastructure and money already in their intellectual property, already in their technologies for 4G. And we're going to leverage that such that they're going to be able to, they're going to develop specifically what we need. We need it for the moon. We need it for very specific reasons and for very specific applications. So we're going to use our resources in the form of money to guide the research so that we get the technologies that we can then, the company is in business to make money. They will then be able to provide to us as NASA and to other space, other commercial entities, other people, that particular technology moving downstream. He says, well, wait a minute, you're giving money to them and then they get the intellectual property. That is true. But if you compare the amount of money that we're giving them versus the amount of money it would require if we did it all on our own, is astronomical. If you're looking at maybe order of magnitude or two. So it's very advantageous it's a win-win. It's advantageous for both of us. It's advantageous for us because we're going to be able to guide and inform and get what we need in the short term for a lot less money than we would otherwise. And the company is going to benefit because they now have an expanded service and an expanded technology that they can put into their business model. So it really is a win-win situation. Awesome. And so that is one way that we use contracts. These are firm fixed price contracts. So you write the contract and we're going to get what we're going to get and what we need. And that is one way that we solicit for proposals, and we get them back. We select and we take it through until we get the hardware or software, whatever it happens to be. That's in the tipping point. The other way that we get these, and we put out other calls that are not necessarily for commercial entities, but they could be. Let's say in the case of Prime, as an example, that this is a call that went out and said, okay, we want to go and explore. We have a need to explore and understand what the volatiles are, and we want to do it on the moon. So there is a group that puts in a proposal. In this particular case, this was led out of Kennedy Space Center, and they put in a proposal. They were selected based on many technical criteria and other criteria, and they have a team and they've developed the technology in-house. Now that's a very different model. That's a civil servants by and large, although they do have contractors. In the case of Honeybee, which is a company that produces space drills. They make drills. So if you're drilling into somewhere and it's happening on Mars or the moon or other places, there's a good possibility that's Honeybee. I said Honeybee is involved, and so they are also a partner in this. And so we put that team together and give them the funding and schedule, and we lay it out just like any other good project does. And we execute based on that, hit our requirements, get our validation, launch, and prove out the technology. And then that's how we advance the technology. And so those are the two ways. I'm sure there are other ways, but I think those are the two main ways that we garner and we get the companies and the academia would be in there as well to help out with our technology gaps.
And continuing along that line, obviously, you're talking about these companies, and we talk about all the exciting things that are happening up there, and ultimately the way they can benefit us in the short term or long term as well down here. NASA has a publication called Spin-Off. It talks about all the stories of these various companies and entrepreneurs that are using these cutting edge projects and products to help boost our economy, help protect the planet. And I think in the current issue, there's something like 45 different companies that, because of the relationship with NASA, have promoted and have these really beneficial tools involved in everything from cleaning up soils to weather forecasting to preventing COVID. Can you just say a few words specifically about Dr. Doug Willard projects that either may be or are already having a positive impact on us down here.
Oh, okay. Let's see here. Well, I'm gonna have to go. What I'm working on now is stuff in the future.
Sure,
So,
sure, I get it. Or anything you want to talk about. Just anything cool that's from the spin-off publication that you want to talk about. No.
Okay, okay. Well, let's see. Stuff that I've worked at. I'm trying to think of not too far back because I worked a lot in shuttle, and so that's a lot of that has come and gone. I did mention solar surfing. I will finish up with that. Okay. And it is under the STMD umbrella, although it is in the NIAC rather than GCD. So but that is what I personally I'm more familiar with. So we are wrapping that up. They come in a phase 1, 2, and 3. Recently, they just have phase 3s. This is a phase 2, and in the next 3 or 4 months, we're going to be wrapping up the final report. We're just now getting through our solar testing. So we basically take a large telescope, but well, not really large, but about that big around, and we track the sun. And the idea is we can scale this with optics to get what it would be if we were, for example, 1 or 2 radii from the sun in a very similar way. Not exactly, it does go through the atmosphere, so it isn't exact. So the scientists out there, yes, I know it's not exact, but it's a good representation of the energy that one would get, that being that close. And I did mention that we got our absorptance back. It looks like we actually have a negative absorptance, which might be confusing to the scientists out there because, well, how would you have negative? Right. We're not violating the second law of thermodynamics. So what isn't known is that absorptance is actually a relative measurement. It's not an absolute measurement, and the relative measurement is based on the NIST standard. The NIST is the holder of standards, and what that means is that we reflect better than the NIST standard, and so that's why you would, if you work it out, that's why you would get a negative value. Got it. And certainly that doesn't mean that's nothing. Actually, having something that reflects better than the standard is something in and of itself. Sure. But that particular ability to scatter electromagnetic radiation or input is right now we're looking at using a very similar orbit as Parker Solar has, going around Venus. It's elliptical orbit around Venus and the sun. And as of right now, it looks like we can put a payload. So the payload, it would be an acceptable temperature range of getting about 2 solar radii away from the sun. So that's 2 from the center, meaning you would be 1 solar radius from the photosphere, if you want to call that the surface. Too deep into it. So you'd be 1 diameter away from the center of the sun, and that is markedly closer than we would have ever come before. Parker, very impressively, is about 8 or 8.5 solar radii, to give you a sense of scale. So as far as what I've done or I'm doing right now that it might be of significance, that may be of significance, but I mentioned earlier, I very much hope to see in my lifetime that mission. But that is well down the road. So that's what I have to tell you.
No, it's awesome stuff, Doug. I know we're coming up against a hard stop for your schedule right now, but I just, listening to you, thinking about what you're doing, not just to get us back into the cosmos, but all the benefits here on Earth are so staggering, and it's fascinating listening to someone like you and your story. For everybody, and I'm going to be rooting you on as you continue to do this role. For everybody that's going to be listening listening to this particular episode across the podcast networks or watching on the YouTube channel. Once again, you've been listening to Dr. Doug Willard, Program Element Manager, Game Changing Development Program, Space Technology Mission Directorate at NASA. Doug, I want to thank you for taking the time to walk us through your story and everything you're doing there at NASA. I want to thank you for doing it, of course. And as we say on this show, thanks for creating a better tomorrow through all your initiatives. A really very fascinating story.
Thank you very much. Had a great time, and I appreciate all the stuff that you're doing, getting the message out. It's really excellent.
Awesome. All right. Good seeing you, Doug. Be well.